Okay, this is the third lecture of the pattern recognition class. To recap, let's see where we are now. In the last lecture, we have learned the supervised learning and descriptive learning. And what is the regression problem? The regression is to relate the input variable to the output variable to either predict the output of new input or to understand the effect of input on the output. So as you can see here, for the input variable xn, the linear regression problem is to predict or understand the effect of the input on the output, called yn, something like this. So this is the regression. So to define the regression problem setting, we need the training data set such as the xn and yn. Xn is the input variable and yn is the output variable. Input variable are also known as the feature covariant independent variable, something like that, predictor, something like that. And output variable yn are also known as the target label response outcome dependent variable, something like this. So to train the regression machine, we need a number of data consisting of the training pair, something like this. So that's why the regression problem is also called the supervised learning problem. Okay, so if we have a data set, something like this, we can represent the data set as a vector and the matrix form, something like this. So in this case, the n is the number of the sample, and each sample consists of the n, what is that, t by 1 vector and y1 output. Okay, so this is the training matrix. And yeah, so to define the regression problem, we need the mapping function or hypothesis, something like this. So f over xn. So in the linear regression problem, we can define this linear mapping function as w0 plus w1 times xn, something like this. So this is the linear equation. It can be represented in this x and y space looks as a straight line. Okay, so this is the simple linear regression problem or linear regression problem setting. Why we use the linear regression setting? Because the linear regression is easy to implement and easy to solve. So we many machine learning methods are based on the linear regression problem. Okay, so and then what was cost function? So if we have the mapping function, something like this, and we have a where is that? Yeah, we have a output value looks like this. So what we want to do is to estimate or fit this mapping function consisting of this parameter. We want to find this parameter that minimize the difference between the estimated values and real values. So this is the cost function. The cost function means that formulate the difference between the estimated and ground truth values. So yeah, there was the cost function like this. There's the cost function should be aggregated across the training samples from n equal 1 through the number of samples, something like this. And the goal of the regression problem is to find the parameter w that minimize the cost function like this. So this is the cost function. So yeah, there are two desirable properties. First one is the symmetry around 0 because the both positive and negative error should be penalized equally. Another desirable property is the cost function should penalize a large mistake and very large mistake similarly, because we don't want to our machine is the overfitted to the very large mistake. So that's why we are proposed to the robust cost function. So yeah, it was the visualization of the cost function. Yeah, something like this. So finally, the cost function looks like this, because when do you see this function? So actually this okay, let's use that, because this function was a linear equation. So this part is also linear equation, right? So if we use the scales of linear equation, it should be what? Second order equation, right? Second order equation. So this term can be represented arbitrary number a times the x square plus p times x plus c, something like this. So this is the general form of this loss function. So what is that? This is the second order linear second order equation. So the shape of this second order equation looks like this with respect to the, where is that? With respect to the W1. Okay. So yeah, let's read it. It is the W. Okay. So because of this generalized term, so the cost function looks like this. So actually in this course we didn't talk about the convexity of the loss function. So convexity is really important property that guarantee there is the global optimum solution among the possible solutions. But so when we see this loss function is this loss function is convex. So it means that we can find the global optimum when we solve the linear regression problem. So today we will see this property more deeply. Okay, so yeah, it was the it was a simplified version of the cost function. Now and then we also talk about the three-dimensional cost function shape looks like this. So when we considering the W0 and W1 as a parameter, we can draw these kinds of surface on the 3D space, and because it is hard to draw every time, so we use the contour plot or contour figures. Looks like this, right? So as you can see here, that this point means the minimum among the possible cost values, or yeah. So there are several kinds of the very well-known cost functions. The first one is the mean square error. The second one is the mean absolute error. So the formulation looks like this and looks like this. So but as we discussed previously, we want to ignore the very large errors from the arbitrary samples. So we need a more robust cost function looks like this. So comparing to the MSE and MAE, like this and like this, the robust cost function looks like this. It means that if there is a very large errors on the training samples, this robust loss function can ignore those very large error samples. But to compute the robust cost function, it is much difficult to compute and write down. So it means that there is a trade-off between the statistical and computational property. So yeah, that's a lowest cost function. So I suggest to you to read this paper to understand what is a lowest loss function comparing to the conventional MAE or MSE. Okay, and then finally we have learned the gradient descent method that solve this optimization problem in an iterative manner. So to solve this optimization problem with a loss function like this, the very fruitful way is to use the grid search. Grid search mean is the compute the every cost on the possible solution and then just to pick the best. This is the brute force, but it was the this is brute force, right? So, but it is extremely simple, but it has too many for loops, so it results in exponentially computational complexity. So we need a more efficient way to solve this linear this optimization problem. So we introduced the gradient descent algorithm where we want to follow the gradient because the gradient is the slope of the tangent to the function. So it points to the direction of the largest increase of the function. What does that mean? As you can see here, if the contour looks like this, to find the global optimum, we should downhill from some arbitrary point. So the best best direction to arrive this optimal minimum value, we can follow the gradient direction looks like this. So this is the main idea of the gradient descent. So yeah, it was the gradient descent. So as you can see here, gradient descent is sensitive to the initialization of the parameter. So when we choose this parameter, the path of the gradient descent looks like this. But when we choose the random variable like this, the gradient descent follow the path looks like this. So that's why we carefully choose the initial parameter values when start the gradient descent. And yeah, this is the algorithmic description of the gradient descent. Okay, so as we discussed previously, the gradient descent algorithm is the iterative solution. So by evolving the iteration, we compute the gradient of the loss function and move to the gradient direction from the previous parameter. Okay, so this is the gradient descent algorithm. We also introduced the learning rate. So learning rate means the magnitude when we move to the gradient direction. Okay, so yeah, it was the intuition of the gradient descent. So this page shows the importance of the magnitude of the learning rate. So if we choose the alpha as a very small number, gradient descent can be very slow, looks like this, right? So but if alpha is too large, the gradient descent can overshoot the minimum, looks like this. Because okay, let's see, because we start from here, and if the alpha is too large, the next step will be looks like this, looks like this, looks like this. So it may fail to converge or even diverge, right? So that's why the choose the proper learning rate is really important, right? So this is the gradient descent. Okay, so it was the last lecture. Okay, let's move on to the today's lecture. Okay, so in today's lecture, we are going to talk about the remaining part of the discriminative learning and generative learning shortly. Okay, actually, in this course, we are focusing on the discriminative learning than the generative learning because actually, as I mentioned in the first lecture, in this course, I want to focus on the deep learning or the neural network or deep convolutional neural network, something like this. So actually, those kinds of the deep neural network are generally based on the discriminative learning. In fact, in recent, many methods are also based on the generative learning in the deep neural network, but most conventional deep neural network are based on discriminative learning. So in this lecture, will study the discriminative learning more than the generative learning. Okay, let's start. Okay, let's continue the regression problem. Okay, so if you remember correctly, there in the last lecture we learned the house pricing prediction problem. So training data was the size of the house with the price of the house, right? So it was the input variable xn, and it was output variable yn, something like this. So the training set of house price looks like this, right? So each these samples represent the sum point on this space, right? So something like this. So this was the training set of the housing price prediction problem, right? So but as you can see here, we just considering the size of the house. So it means that this is the single feature or single variable to predict the house of the price of the house, right? So what we want to do now, we want to deal with more parameter, more features or more variable. What does that mean? So to decide the price of house, something like this, not only considering the size of house but also considering the several factors like the number of the bedroom, number of floor, the age of house or age of age of home or age of house, something like this. So considering the whole of the features to predict the price of house would be be much accurate than only considering this single feature, right? So because we have the more information than the single feature, right? So that's why we introduce some multiple features or multiple variable. So as you can see here, so it was the input variable and it was the output variable in the previous example, but we introduced the further inputs looks like this. So we could represent like this is the input 1, input 0 and input 1 and input 2 and input 3, something like this. So it means that we can represent our input features as a vector of those feature, right? So it means that this is the first sample of the input variable looks like this. So it means that, okay, if we consider this value, it can be represented by one subscript 1 with a superscript 2. So it means that this is the value of features 2 in first training sample. First training sample. So it's like this. So if we considering the multiple feature, we can represent our input variable as a vector x, looks like this. Okay, let's see the detail. Okay, so yeah, let's see here. Okay, so it means that we can represent the training data as x and matrix y, looks like something like this, and to represent the input variable matrix x, we can just to copy this value, looks like this. So it should be 2001 045 145 3 2 40. This with the y is equal to 460 232, something like this. So now we can represent the input variable in a matrix and vector form like this. So okay, now we have a multiple variable, so we need a new mapping function than the previous one. Actually, in the last week we learned the mapping function, or the model of the linear regression looks like this with a single variable x, right? Now we have the multiple variables, so we need a additional mapping function. So because we have four kinds of input variable, so the mapping function can be represented looks like this. So yeah, use this. So this is the input 1, input 2, input 3, and input 4. The estimated value should be represented by this four kinds of x variable, input variable, or x variable with the coefficient, something like this. Actually, we introduced this coefficient to consider the bias term. We will discuss this in the next slide, but so we can just represent this mapping function of the multiple variable looks like this. Blah 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 blah. U4 times x and 4. Okay, so if we assume the x and 0 is equal to 1, we can just represent the mapping function in a general form, looks like this, right? So this is a mapping function for the multiple features in the linear regression problem. Okay, so for example, if we determine the parameter W0, W1, W2, W3, W4 as a 80, 0.1, 0.013 minus 2, then the mapping function of this regression problem looks like this. Okay, you should be careful when see this number. Actually, it's not a scale. I mean, this number 2 means the second, where is that? Yeah, second position of the feature. If you it make you confused, I would say you can use the addition another rotation looks like this. Okay, so please be careful. This is not the scale. Okay, so okay, this is the notation of the multiple features in the linear regression problem. Okay, so we have a mapping function looks like this. So we need a more convenient way to represent the mapping function between input and output variable. So let's say, yep. Where is that? Okay. Yeah, it should be x0. Okay. By the way, that's why you should learn you should watch this video, because if you don't see this video, you cannot find the errors on the slide, right? So you should watch this. Okay, so it means you are very lucky to find the error. Anyway, so this is the mapping function like this. We can represent our multiple input variable. So what does that mean? So multiple input variable can be represented in a vector notation, right? Like this. So we can say that the vector x is equal to x1, x2 through the xn transpose lying in the real number superscript n plus 1. What does that mean? Do you remember the vector notation, right? So if you are not familiar with the vector notation, please watch the first lecture of this course, so you can find what is the meaning of this notation. Okay, so it means that the vector x, size of vector x is n by 1. It means that there is n rows with a single column. So this is the vector notation. Similarly, we can represent the what is that? The parameter that describe our mapping function looks like this. The size of this vector of the parameter are same as the input vector, right? Okay, so if we introduce these two kinds of vector notation, we can just represent this mapping function looks like this. Okay, so this is a very simple dot product, right? I guess all of you know what is the dot product, but if you are not familiar with the dot product, please go back to our first lecture. So to recap, the dot product looks like this. So the transpose of the W should be W1, W0, W1 through the Wn, and the original matrix X should be X0, X1 through the Xn, like this. So it should be X0 times X0 plus W1 times X1 through the Wn times Xn, something like this. Because we assume or we define X0 is equal to 1, so this is exactly same with this mapping function, right? So this loss function, no, it's not a loss function. This mapping function is called the mapping function for multivariable linear regression problem.